All right, and we are live. Welcome to Business Analytics 6356. Great to have everyone here today. Sorry for the short delay, as I'm sure it is with many of you. Life is life sometimes, and life can be a bit hectic, but I'm really glad that we are able to be here tonight together on what is, I don't know, maybe our fourth, maybe our third lecture. My numbering gets a little bit weird right now because I know the asynchronous lectures and what I report right here says this is lecture number 4. Of course, this is just our third night together. And so what happened there is when I originally recorded these videos a couple of years ago, the course was offered on Monday nights. And the third Monday of that semester was the Labor Day holiday, and so class didn't meet. And so in my infinite wisdom, I numbered the videos as 1, 2, skip 3, and then 4. And now in most subsequent semesters, this is actually our third time together, but I try to keep the numbering in sync with the asynchronous videos. So now that I'm a bit older and wiser, whenever I number my lectures and my videos and things like that, I just go sequentially by the number of times we've been together, not the week of the course, but you live and learn, and when eventually these videos are re-recorded, we'll redo the numbering. But regardless of what we think the class number is, today is September 9th, 2025. Great to have you all in the Zoom room with me again tonight. And tonight is going to be our introduction to our first non-relational database management system of the semester, Apache HBase. So in the first week, we had a little bit of kind of general motivation of why we have developed non-relational database management systems, and we talked about web scale data and things like that. And then we we kind of revisited relational databases and kind of extended our understanding and looked at some really interesting kind of additional functionality that Postgres gives us with fuzzy searching and phonetic matching and doing the Levenstein distance and hypercube analysis and stuff like that. But now we're moving into our non-relational database territory. So in preparation for tonight, you should have watched video series 4, which gave you a little bit of an introduction to HBase, kind of a high-level overview of the architecture and purpose of HBase, but then getting into kind of the create, read, update, and delete operations, so some basic interactions. And in this, should have read chapter 3 in the Perkins 7 Databases in 7 Weeks book. And really what we're covering this week corresponds with day 1 of that week-long coverage of HBase. And then next week, we're going to be getting more into the HBase architecture and the programmatic access of data with HBase instead of as much of the interactive stuff. So doing our create, read, and update and delete stuff. And then also, you should have read chapter 8 in the Harrison Next Generation Databases book, right? So that was kind of the content to prepare. The videos were, as it says here, about 47 minutes in length. So I expect class tonight will be somewhere around an hour and a half to 2 hours to kind of round out our 3 hours of instruction for the week. But in the Harrison Next Generation Databases book, I think this is a really interesting chapter in which he talks about different distributed computing models. And there's a lot of reasons we would do distributed computing above and beyond just data management. But of course, distributed databases are a very big topic for modern, globally distributed applications and dealing with big data and all the things that we talk about in this course. So Harrison talks about these kind of 3 distributed computing architectures where we talk about computer systems having either a shared everything architecture, a shared nothing architecture, or a shared disk architecture. And so when we pause 1 second, I have something reverberating over here. Give me one second. All right, I'm back. Sorry about that. Those of you that have had me, especially in a face-to-face class before, might recall that I have a lot of music-based examples because I really enjoy music and I play a little music myself, and I am actually surrounded by, I know it looks like I'm just in a white infinite void here, but I actually have a few guitars around the room, and one of them was positioned in such a way that I think it was catching my voice, and the strings were kind of just droning a little bit as I talked, and it was very distracting, and I don't want to be distracted while I'm talking to you. I want you to have my complete focus. So I'm back and I'm focused. All right, so we talked about these 3 distributed computing architectures: shared everything, shared nothing, and shared disk. And so the way we typically think about kind of our simplest approach to computing is the shared everything architecture. And in a shared everything architecture, all of the services running within your system all have access to all of the CPU, memory, and disk resources, right? We're sharing everything with the service that is running. And in practical terms, the only way to have a shared everything architecture is when everything is running on one single server, right? And this is the way many services ran for many years before we had to start kind of scaling out and spreading things across clusters of multiple servers. But as we discussed in the very first night of class, if you are running all of your services, all of your databases and things like that on one single server, and you need more performance, the only way to gain that performance is by scaling up, right? We can add more CPUs and faster CPUs and more memory and more network throughput, more disk, stuff like that. But this results in a couple of problems because there is only so far you can scale up. Right? There is only so many CPUs you can put into one physical piece of computer hardware, right? So we hit a limit with scaling up. And then additionally, when we scale up, if we have just one server that's getting bigger and bigger and bigger, we're kind of putting all of our proverbial eggs into one basket, right? We introduce a lot of risk there. And if that one server crashes or has some kind of problem, then our entire database becomes unavailable. Also, scaling up doesn't do anything to address the issue of like distributed users, right? If we have one giant server located in Houston, Texas, that'll be very fast to access for customers in Houston and maybe even San Antonio and Dallas. But the further you physically get away from Houston, where the server is located, the slower your access is going to become. And that's not good for globally distributed applications. In modern application design, where we plan on having users all over the world, we want to have distributed systems so that users can connect to a server that is physically near them. It just gives them better performance. So scaling up doesn't help with that at all. So for modern distributed applications, for like really big data things, instead of scaling up, we typically think about scaling out, right? Instead of having bigger and bigger servers, we have more and more servers, right? And this is where we get into the shared nothing, or in the case of HBase, a shared disk architecture. Okay, so everything we talk about in this class, with the exception of HBase, is going to use this shared nothing architecture, right? Where every node in your database environment has its own CPU, memory, and disk resources, and none of that is shared with the other servers or with the other nodes in your database environment. But since none of these resources are shared, well, then how does the data get synchronized between them? Well, we synchronize that data by copying it or replicating it over the network, right? And when you're talking about writing data to one server and then you have to replicate that change through the network, there is necessarily going to be some delay, some period of time where that update has occurred on one server but is not on all the other servers yet. Right? We have a state of inconsistency within our database environment. If you were to ask one server the answer to a question, you get one answer. And if that hasn't replicated to others, you'll get another answer from different servers. Now, in a situation where all of your servers in your database environment are perhaps co-located in the same data center, right, in the same facility, that latency may be on the order of like a few milliseconds. It might be completely imperceivable to humans and not a big deal at all. But when we start talking about distributing databases across multiple cities, multiple states, multiple countries around the world, then it is very possible, even likely, that when you make an update on one database server, it would take a second, a few seconds, maybe even a few minutes, depending on kind of the configuration of your replication scheme, for that update to show up on all the other servers. And depending on your use case, depending on the business problem, depending on the criticality of this data being up to date, right? You might have different kind of levels of acceptable states of inconsistency, right? I mean, if you think about like a Twitter or Facebook or something like that, and you've probably experienced a time when you look at Twitter and your friend is looking at Twitter and looking at the same posts, looking at the same things, and you see something updated just a couple of seconds before they do, right? This is a state of database inconsistency. And in that use case, like, it doesn't really matter if not everyone sees the same tweet at the exact same second, right? We can delay this by a few seconds and still be fine, but it just depends on kind of the business case. But we have a lack of consistency in these shared nothing architectures, right? And this is one of the trade-offs between relational databases and non-relational databases, right? Non-relational databases, we get this global scalability, but less consistency. Harder to scale a relational database, but we have strong consistency. Now, the shared disk architecture is kind of a special case in the middle, in which each database server, each node in your environment has its own CPU and memory resources, but there is a shared disk infrastructure that all of your database servers are connecting to the same hard disk, the same storage device, right? And in this case, or in this manner, HBase is able to give a guarantee of strong consistency, much like a relational database, right? Because there's only one copy of the data being stored in this distributed storage environment, and all of the potentially hundreds or thousands of nodes in your HBase environment are accessing the same shared storage. So we get consistency, but we get the ability to scale out very wide, to have many, many nodes, many, many servers in our distributed database environment. And one of the caveats to this, one of the kind of tricky things about doing this, is all of these servers do have to be like co-located in the same space, right? We can't like globally distribute our stuff. So we're looking at kind of different types of problems we're solving with HBase than many of our other non-relational databases. But nonetheless, it's an amazing system for dealing with really big data problems. And this shared storage infrastructure is facilitated by the use of the Hadoop platform. So HBase is pretty tightly integrated with Hadoop, which is this basically like a clustering environment where we cluster together multiple servers. And then as part of Hadoop, there is a file system called HDFS, or Hadoop Distributed File System. And that's how HBase is able to have this shared storage situation going on. Whew, boy, that was a lot of talking I just did about chapter 8 of this next generation database book. I must think it's really important and exciting. Obviously, I do, and I hope you also enjoyed reading that content. But yeah, so that was your preparation for tonight. And my clicker has now wound up on the wrong window. There we go. So in addition to doing that, hopefully you also had an opportunity to install an SSH or secure shell client like PuTTY. I'm going to be using PuTTY throughout the class for connecting to the Linux servers that we're going to have to be using throughout the semester. There's also an SSH client built into Mac OS and into Windows, but just because PuTTY is available on all operating system platforms, so we have some consistency. Also, the file transfer, I think, is a little bit easier with PuTTY than some of the other SSH options. That's what I'm going to be using, but any SSH client really will work. So installed and configured PuTTY, and then connected to our shared HBase server. And I sent you out a couple of days ago the connection instructions. You use the same username and password that you used to connect to Postgres. And for all of our databases going forward, we'll just use that same username and password, but there will be kind of different connection methodologies or instructions for all of them. And then if you're really feeling good about things, maybe you even watched the kind of tutorial video of installing or configuring HBase inside the Amazon Elastic MapReduce environment. And this is an optional thing to do, just if you're kind of interested in cloud computing. And I noticed a couple of semesters ago now, some of the workflows, some of the clicking is a little bit different than exactly what I do in this video because AWS is constantly kind of updating the way things work. But it is pretty close, would give you a pretty good idea of what to do. But you don't have to do that by any means. We have a shared environment that the university is paying for and all that for you to connect to for absolutely free. So that's that. And then also, I checked a little earlier today and it looked like most all of you, or all of the groups anyway, had submitted assignment 1 where you were using the U.S. counties data set to find counties that were similar in whatever way you deemed important to Harris County, Texas, and Davidson County, Tennessee. And I just quickly skimmed through a couple of the submissions earlier today, and I was, I think, very pleased with a lot of what I saw. So I really look forward to digging into those just a little bit more over the next couple of days, and I will be sending feedback on that. All right. Whew. So what we're going to be doing tonight, kind of a brief recap, kind of a getting us back in the right mindset, up to speed about the asynchronous videos. And then we're going to do a little bit of kind of comparing and contrasting of the performance of HBase compared to Postgres, right? And we're going to see that for some things, and this will be even more evident next week when we start looking at more complex queries in HBase, but in some cases, HBase will be much, much faster than the equivalent commands in Postgres, and in some cases, it will actually be slower, right? So we have to kind of understand the appropriate use cases here. So we'll demo that. We'll have a poll everywhere activity to prepare us for Progress Quiz 3, which will come available on Canvas in just, I don't know, an hour or so from now. And then we'll close up the evening with a little bit of a discussion about what you will be expected to do for the case project. The first rounds of the case project presentations coming up on October 21st. All right, any questions, comments, concerns before we kind of click over into our content for the evening? And remember, as always, you're welcome to unmute yourself and unmute your video, the whole thing, and we can talk like that, or you can always drop questions and comments in the chat window that I have pulled up here. But hearing and seeing no comments, we'll go ahead and get started here. So, 5 genres of database management system. We have seen this slide, I guess, 3 times now in the introduction content when we described our relational database of Postgres, and now a 3rd time as we are starting to describe Apache HBase. So as I mentioned, we'll kind of start here with each one of our database management systems. So Apache HBase is a column family database, also sometimes known as a wide column database, sometimes known as a wide row database, right? A couple of different ways that this is described. And as we mentioned in the asynchronous videos, and we'll kind of quickly review tonight, it is important to make this distinction that there is a different type of relational database called a columnar database, which is not the same as a column family database. So be on the lookout for that. What drove the development of systems like Apache HBase? Really, it is dealing with the biggest of big data, like web scale data, Google scale data, where we're talking about like hundreds of millions or billions or even trillions of records that we need to be able to, sort through, search, manage, retrieve, all that. And the reason I kind of bring up Google here is that Apache HBase is an open source implementation of Google's Bigtable database. And Bigtable is what kind of powers all of Google Search, Google Maps, Gmail, stuff like that. And as I was thinking about Gmail and like the scope of what is big data, what is Google level data, I'm like, well, how big is Gmail really? And of course, like no one, maybe outside of Google, like really knows, but maybe we could kind of infer a little bit. So I did a little bit of Googling, and according to the internet, there are about 1.8 billion, with a B, users of Gmail. 1.8 billion users is a giant number to begin with, right? And so 1.8 billion users. And I went and looked at the number of messages in my own Gmail account, and I have 34,000 messages stored in Gmail. And that's not 34,000 unread messages. Like I have a little bit better email hygiene than that, but I have had this Gmail address for 21 years actually now. So I've had it a long time. I have a lot of sent messages, a lot of archived messages, a lot of things like that. And I am sure there are some users that have more than 34,000 messages and some users that have fewer than 34,000 messages. But my Gmail is about 60% full. So I don't know. I feel like maybe we could assume that's an average-ish number of messages. So if you say there's 1.8 billion users and an average user has maybe 34,000 emails in Gmail, well, that works out to 63 trillion with a T, 63 trillion emails that are stored in Gmail. 63 trillion is a tremendously, almost incomprehensibly large number, right? But yet, when you go to Gmail and you log in, your email pops up pretty much instantaneously, right? It's not like a long search process. Or if you click on a particular label, or if you search for something, or when you open a specific email, it's essentially instantaneous, right? It's in just a few milliseconds that actually is displayed to you. So think about that one email among the 63 trillion emails that Gmail manages. I mean, that's like the needle in the haystack kind of problem. But that's exactly the kind of problem that a system like Apache HBase or Google's Bigtable database was designed to deal with. right, was finding one specific message among a sea of many, many, many other messages, right? And you could kind of think of like web search in the same way, right? Or think about all the different locations that are being tracked in a service like Google Maps, right? So dealing with really, really big data is what we're talking about here. We're going to interact with HBase using kind of a combination and variety of kind of programming languages and commands that are based on programming languages, but all kind of related to Java and JRuby. And then next week we will be introducing a kind of SQL-like language called HQL or Hive query language to interact with HBase. But there are some pros and cons to that. It's not all roses when we start doing that. There are some performance implications and things like that. But by and large, it is not terribly easy or like user friendly to interact with HBase. Like your basic create, read, update, and delete commands are pretty straightforward, but when you get beyond that, some of it gets a little bit hairy. And then when you start getting into the documentation, it can be pretty technical in nature. So, very much this is kind of designed to support like back-end processes more than being something that we regularly interactively interact with, which is the way most databases kind of work. But we're going to see some pretty gnarly syntax and commands and stuff like that. What makes it unique? This tight integration with Hadoop and HDFS, which we talked about, just a moment ago for our shared disk infrastructure. The ability to handle just massively big data, right? And we'll talk about big data with all of these databases, but something like HBase really just kind of is in a different class of big data. And then it has some nice features around like the automatic creation and capture of metadata and version control and things like that we don't typically find in a lot of other database management systems. So that's kind of neat. Performance-wise, it is really good for really big queries on really big data sets, right? It's all about big data. So it scales up very well, but doesn't really scale down to small queries very well, right? And one way I kind of think it's interesting to think about this is because of this distributed nature, there is a lot of overhead to starting a query. But once the query starts running, it's very, very fast, right? So if you think about, something like in the real world, is it faster to drive somewhere or to fly somewhere? Now, airplanes clearly are much faster than cars, right? But it's not always faster to fly. And think about if, I'm here in Houston and I want to go visit the Alamo in San Antonio, and I just mapped this out a little bit earlier today. Door to door from my house to the Alamo is right at 3 hours, okay? The flight from Houston to San Antonio is only 1 hour, right? So that seems a lot faster, but you got to consider to make that flight, I have to drive to the airport, which is going to take me 30 minutes. And then I've got to park and I've got to take the shuttle to the terminal, which is going to be like another 30 minutes. And then I'm supposed to be at the airport an hour before my flight. So there's another hour. And then I fly for an hour, so there's another hour. And then I get to the airport, I got to rent my car, I got to drive to the Alamo, so that's going to add like another hour. So really, at the end of the day, it would take me like 4.5 hours to get to the Alamo if I fly versus 3 hours if I drive. But if I'm going to like Los Angeles, then it's going to be much faster to fly, right? Because the overhead, the startup costs kind of stay the same. And then the for the longer distance, the flight is going to be a lot faster than driving, right? So that's kind of the similar situation with HBase. When we're doing small things, there's a high startup cost that a relational database doesn't have. But when we're running big queries, that high startup cost doesn't matter as much because it's a much smaller percentage of what it is you're doing, right? So yeah, it scales up very well, doesn't scale down very well. And then we're also going to find next week in some of the examples that if we start looking at more complex things and calculations and aggregate queries and things like that, the performance gets even worse because that's just not what HBase is really designed to do. So stay tuned for more discussion around that. All right, so column family databases. There are some elements of this that are a little bit confusing, and part of the confusion that we're going to encounter is because in many ways, column family databases kind of look and act a lot like a relational database. Unlike everything else we're going to talk about this semester, column family databases are tabular in nature. They are table-based, much like a relational database is table-based, right? So we talk about tables, we talk about rows, things like that. So at a glance, it looks kind of similar, but we wind up using the terms and kind of operationalizing things quite a bit differently. And then the other piece of confusion that I mentioned earlier is there's a different relational database technology known as the column store database. And when you start Googling like column databases, people will kind of conflate column store and column family databases and think they're talking about one when they're actually talking about the other. And you might find information that contradicts what we learn in this class, not because it's like really contradicting this, but because they're confused about the difference in a column family and a column store databases. So people start using these terms interchangeably, and then it gets very confusing. But for column family databases, what we're talking about in this class, things like Google's Bigtable, HBase, and Cassandra, data is stored and accessed as rows, right? We sometimes call this like a row store, and I said that we call this a wide column or a wide row database sometimes. And in your physical schema, in the architecture of how data is stored to disk, your values are stored like physically together by the row with kind of the use case assumption that when someone asks for data about a customer, it's most likely they're going to want all the data about that one customer, right? That's kind of the row mindset that relational databases and column family databases are built around. In a column store database, however, your data is physically stored together by the column or by the attribute rather than by the row or the instance or the tuple, right? With the kind of business problem, the business mindset of we're going to be asking questions about a particular value of an attribute across all observations in this database, right? So if you think about something like a retailer who might be selling, might have millions of customers, right, and millions of sales, and they want to calculate the, average spend across all of their customers, right? What we're really interested in there are not those individual rows, but you're interested in all the values of a particular attribute, right? Like total price paid, like invoice price or something like that. And so that is where a column store database really excels, right? That's not the topic of this class, right? And when you start seeing people talking about things like Sybase IQ or Vertica or MonetDB or CStore, that's the other thing. That's a column store, not a column family database. So One point that could be a little confusing as you are like Googling and troubleshooting and stuff like that. And we walked through this example in the asynchronous content, so I'm not going to kind of continue to belabor the point. I just want to kind of bring that up to make it a little bit front of mind. All right, so in a column family database, and here we see kind of an example with some dummy data similar to what we'll use or what we used in the asynchronous videos and kind of revisit a little bit tonight. We see what looks like some rows, right? And we see some values. We see some things that look like attributes, perhaps. Like this is kind of familiar looking, kind of looks a little bit like a relational database. But we're going to point out kind of where we start to diverge, where things get a little bit different. So in a column family database, we do still have a schema. We talked a lot in the relational database class about defining your schema, right, and designing your database before you use it. However, we're going to find with many of our non-relational databases, we do not have a schema at all. We don't do any definition of what our data look like before we start putting the data into the database, which seems really strange. But in HBase, in a column family database, we do have a little bit of a schema. We might consider this kind of a weak schema or a very loose schema in which we define not individual attributes like we do in a relational database, but we define some column families. Okay, so in this case, we have 3 column families, customer details, relatives, and accounts. And then we have a row key that is our unique identifier. Okay, so when we define a schema in HBase, all we define is the name of the table and then the column families. We don't define any of these individual what look like attributes, but we're going to call column family qualifiers ahead of time. We only define these column family qualifiers as we actually start writing the data into the database. And every row in our database can have a different set of column family qualifiers within these column families. So if we kind of compared this to a relational database, we might think of this as like every row in our relational database has a different schema, a different set of attributes than every other row in the database, which is a really weird way to think about things, right? So, we have, in some cases, customers all have this customer details name qualifier. Okay, that's the same in all of them. Doesn't have to be, but it is. Some of our customers have a qualifier called nickname, right? Some have a column family qualifier called maiden name. Some have a mobile phone number, right? Some have a home phone number. Some even have a fax number because they're still stuck in like 1995 or something like that, right? But notice that some customers don't have these column family qualifiers, right? Some customers have qualifiers as part of the relatives column family. Some do not because they don't have any relatives. We have a lot of sparse data here. And sparse data is not great when we have a relational database because when we don't have a data value in a relational database, we have to put a null value there. And we talked last semester a lot about how null values kind of make our data trickier to work with. And if we have a lot of null values, it's often indicative of bad database design, right? But HBase is great at dealing with sparse data and is not ever going to have any null values because if we don't have a value for a particular column family qualifier, we just don't have that column family qualifier. If we don't have any data for it, we don't create that column family qualifier for that particular row. So it actually makes it really, really good at dealing with sparse data, right? And we could, at any point, just add additional qualifiers for a particular row, basically add additional attributes. So if we decided we wanted to start keeping track of our customers, social media accounts or something like that. We don't have to do any kind of database like redesign. We don't have to add attributes or anything like that. All we need to do is update this row with a new qualifier and it's there, right? So it gives us a lot of flexibility. But then on the other hand, we never know whether a particular row is going to have a particular column family qualifier. It's going to have any data for that thing that we are looking for, right? So it makes searching a little bit less efficient. It can make it harder to kind of identify particular pieces of data, things like that. So generally the way we're going to interact with this is just by asking for the entire row that's associated with this row key, and we get the entire like set of data back from HBase, and then we kind of parse it as we see fit. So just a different way of thinking about our interactions. This is basically what we just kind of said here. So, one more thing I will say about this schema though. So, we have this kind of weak schema that defines generally what a row is going to look like. We're going to have some details about the customer, about their relatives, and about their accounts. The other thing that the schema is good for in HBase is this kind of sets up some kind of describes to HBase how the data should be organized in order to enhance the performance, right? So when you create a column family, all of those, the values of all of those qualifiers are going to be physically stored together in the same region so that it's faster to bring back all of those values at the same time. That's the other important thing that the schema does in HBase. It helps with the performance. All right. So yeah, all of this is kind of covered in the asynchronous content, so I'm not going to belabor the point anymore here. But we are going to jump right over into PuTTY using SSH to connect to our Linux server that's hosted in the AWS cloud and a data center somewhere in the middle of Ohio. So we're going to get this kind of interactive experience and make sure everyone is kind of understands what we need to do to connect to HBase to start really using stuff. So we're going to be connecting using PuTTY via SSH or secure shell. This is a technology that has been in heavy use for the last, I don't know, probably 25, 30 years. Like it is just kind of the default way that people connect to typically Linux computers or Unix computers over the internet, although there's other things that we can use it for. But effectively what happens is when you connect to a machine using SSH, it creates a secure encrypted tunnel over the network, and in this case over the internet, between your computer and our database server that is in the AWS cloud. So once you've established that tunnel, everything that you are like typing into PuTTY is being sent through that encrypted tunnel to the server that's in AWS, and then that is executing your code, and then you're seeing the results come back to you. So once you have PuTTY installed on your computer, this is what the connection screen looks like, except you won't have all of this stuff down here. This will be blank for you. I just have several different servers that I connect to for various things. But basically, you just put the connection information of the HBase server right here, which that's the IP address, but we could also do the host name that I sent to you all. If you want to save yourself a little typing, you can click save to save this as a profile. But we do this and we hit open, and the first time you connect, you may get a message that says something like something about the fingerprint not being stored in your local cache. Like, do you want to save it? I would suggest just saying yes, save it, and then you'll only get that error message one time. That's just like a putty security thing. But once you do that, you'll get this prompt that says log in as. And so this is where you're going to put the username and password, same thing you use to connect to the Postgres server. So I'm going to log in as M. Grimes, and then it'll ask you for a password. And here's the thing that often confuses students, but this is the way that most, I think virtually all, Linux and Unix servers deal with passwords, is when you type something in right here, you're not going to get any response at all from the server. You're not going to get dots or asterisks. You're not going to see what you're typing. It's just going to be completely blank. And you just kind of trust that your keystrokes are being sent to the server. And then when you hit enter, it will kind of validate and let you in. So I'm going to type my password here. I hit enter. And we're greeted with this kind of clever looking ASCII art that says EMR. That stands for Elastic Map Reduce. That's just the Amazon platform that HBase is running on top of. Okay, so now everything that we are typing into this window right here are commands that are being executed on this AWS EMR instance that's running in a cloud data center, again, somewhere in Ohio. So this is Linux. Okay, this is very similar to being at the command line in a Windows machine or at the terminal if you're an Apple user, right? So you're going to type your commands in here, and something is going to happen, right? So if you wanted to, for example, see the contents of the directory or the folder you're in, the command for that is ls, which is short for list. That's very similar to like the dir or directory command in Windows. So here you can see these are files that I have uploaded to the server for the various demonstrations and projects and stuff like that that we're going to be doing. If you type pwd, that stands for print working directory, and this tells you what directory, essentially what folder you're in on the server, right? So in this case, I am in a folder which is home/mgrimes. Okay. On Linux, you don't have a drive letter like C:, D:, whatever. The // is just like the beginning of the file system, and then there's a folder or a directory called home, and then inside that there's a directory called mgrimes, and that is my like personal, private, secure file storage area. Okay. Now, if I go up one level in our directory structure, I can type cd space ... and that will move me up from my home mgrimes just into the home directory. Okay. So now I'm at just /home. And if I were to do ls here, you see that I have created, when I created the accounts for you to log in here, it automatically creates a home directory, automatically creates a folder for each one of you. And I can't I don't think anyway, that I can go into, your individual folders, right? Permission denied. So this is like your own kind of private area on the server for uploading files, and other people can't interfere with you. Now, I could interfere with you, like I have the super user administrator stuff or whatever on here, but this is kind of like, keeps you segregated from the other students in the class. So when you upload stuff to the server, and this is the case for HBase, and this is also the case when we start doing similar things using like CouchDB and MongoDB and Postgres and all that, you're going to upload to your private directory on the server, and we'll get familiar and comfortable with that soon enough. All right, so we're connected via SSH to our EMR server that's running HBase in the AWS cloud. That's a lot of alphabet soup coming at you right there. And so when your prompt looks like this, so it's like username at, and then this is the private IP address of the server, you're just like at the Linux command prompt. You are just running commands on the server. You're not actually in HBase yet. To get into HBase, you type HBase shell, and this is the HBase like client that we're going to be using. Okay, kind of like we use SQL Workbench to connect to Postgres, we're using HBase shell to connect to HBase. And when we run this, there's a whole bunch of error messages that come spinning across the screen. That is just a result of kind of the way EMR is configured. And I can't figure out a way to give you enough rights on the server that you don't get these weird error messages without giving you enough rights that it kind of would allow you to destroy the world, to kind of shut down the entire environment. So just ignore the error messages and know that if you were using this like at work in a production environment, you probably wouldn't have all these weird error messages spinning across. But now that we are in HBase shell, notice that the prompt you're at is a little bit different, right? It says HBase main, and then this number, I think, kind of increments as you run commands, right? So if it says HBase, you are in HBase. If it says your username at IP address, then you're at the Linux shell, right? So I exited out of HBase. I need to get back in. All right, so we're gonna kind of review some of these create, read, update, and delete operations. And of course, this is all in the slides that are already posted to Canvas, so you can kind of copy and paste, follow along as you see fit. But once we're in HBase, if we type list, we see a list of all of the tables that have been created so far. And I mentioned this a little bit in the connection information that I sent out. The way the security is configured in HBase, I can't like totally segregate you like I could in Postgres. So you will see the tables that other people in the class are using. And in fact, you can even delete them because I can't give you rights to create a table without also giving you rights to delete the table. So please don't do that to each other. Don't disrupt each other's work. However, you wouldn't be able to read anyone else's table, right? So I see one student here has created a table for themselves. That's awesome. So if I were to try to read from that table, using the scan command. Did I spell that right? Okay. If I were to do this, I'll get an error message saying that I don't have rights to do that. As opposed to if I did a scan on this table that I created, I have rights to see all this data, right? So there's a little bit of control there, but just be kind to one another. Don't do anything disruptive. And man, that's a lot of stuff spinning across. Okay, good. That finished. All right. So in the asynchronous content, we looked at kind of our create, read, update, and delete operations. So we said in order to create a new table, we need to specify the name of the table and then the column families, but not the column family qualifiers. So we would just say something like create MG customers and then details, relatives, and accounts. And every element in pretty much all of our HBase commands are wrapped in these single quotes. So we're going to see a lot of single quotes as we are working with HBase. So when we do this, it's going to create the table. And that took 1.263, about 1.25 seconds, which for a human being, I guess, seems kind of fast. But that is an absolute eternity in computer time. By contrast, creating a table in a relational database like Postgres might take about 0.1 seconds, so about 100 milliseconds to create a table, whereas this took about 12 times that long, right? And this is one example of kind of this overhead where, since we are in this distributed clustered environment, when we create a table, when we delete a table, if we make any kind of modifications to a table, things like that, HBase has to like kind of stop and reach out to all of the other servers, all the other nodes in this environment, and coordinate that creation. Now, other things like reading data can be much, much faster, as we'll see, but then some things are much, much slower, and this is just kind of an example of that. But at this point, we now have this new table that I've just created, MG customers, and we could put some data in there using our put command. So I'm going to say put into MG customers, and let's, I think the row key was 101 in the example that we had earlier, and into my details column family, we're going to create a column family qualifier called name, and we'll give that the value of Adam, right? Now if we say scan MG customers, we see that row 101, this is our row key. We have a column family of details with a qualifier of name and a value of name that is Adam, okay? And then also we have something that we didn't intentionally write to the database. We have this timestamp. And this is what I was talking about, kind of the neat metadata and the version control that HBase just kind of automatically does for you, is it automatically creates a timestamp of when this data value was written. And HBase can also kind of optionally, and this is discussed in the asynchronous content, keep multiple versions of values. So as you change, you add, you write new data, stuff like that, you can kind of roll back to previous versions if something goes wrong, which is much more complex, and you usually have to have kind of out-of-band processes to do that in other databases. But it's kind of neat that that's just built in. However, you may be looking at this and going, well, you say this is the time that this value is created, but Professor Grimes, 1757462443639 isn't a time I've ever heard of. And yeah, that's kind of weird, but this is the way that most computer systems deal with time, right? Whereas you and I think it's 7:02 on Tuesday, September 9th, 2025. That makes sense to us as humans. Computers understand time, generally speaking, as being the number of milliseconds or thousandths of a second that have occurred since midnight on January 1st, 1970. Super weird, I know, but from a computer's perspective, midnight on January 1st, 1970 is like the beginning of the universe, the beginning of time, and we've just been counting up ever since then, right? So this is called the Unix Epoch Timestamp, EPOCH. And it has a lot of benefits, like one, it's not impacted by things like time zones and leap years and things like that. If we want to compare two dates, right? If you want to know the number of minutes between now and Friday at 3:04 p.m., it's just a simple subtraction of these two values, right? So it really makes organizing things by time a lot simpler for a computer. And if you just Google Unix Epoch timestamp, you'll find a web page. This is the first web page that comes up that will make these conversions. And if I just paste that value that we just saw right over here, just paste that in here and say convert that timestamp to a human date, you see this corresponds with, in my time zone, Tuesday, September 9th at 7 o'clock and 43 seconds and 639 milliseconds, right? This is down precise down to a thousandths of a second. So that's the time on the server when this record was created. So we'll actually, throughout the rest of the semester, see this idea of the Unix epoch timestamp come up kind of again and again. Like it's a very commonly used things in a lot of applications like that. So I just wanted to take a moment to kind of point that out. But of course, like we saw in our asynchronous content, we can insert a bunch of additional rows here, and like usual, I just have a text file that I'm kind of copying and pasting from here, but the same content is in the asynchronous slides that are already posted. So we updated a bunch of things here. One issue with interactive interactions with HBase using HBase shell like we're doing here is that we are limited to inputting one value at a time, right? So in SQL, in an insert statement, we could insert any number of values for any number of attributes. We have to do things one at a time here. And note that when we do that, gosh, it's kind of hard to see. Can I make my screen wider without messing things up? Yeah, it's still okay. Note that every timestamp is a little bit different, right? Because it took, 14 thousandths of a second to input this value before we got to this value. So we get kind of slightly different timestamps, which in some use cases might be not a very good thing. So we'll see next week when we're talking about programmatic access with HBase, how we can write kind of small applications to encapsulate multiple values and insert them all at once, and you would have the exact same timestamp. But just one of those things that can be a potentially a little bit of a challenge, something to kind of look out for. Also, as described in the asynchronous content, let's look at just one particular. So if we say get from MG customers, let's say row key 103, right? So scan is like doing a select asterisk from table in SQL. So scan is showing us everything. If we use the command get, and then provide a row key that we're interested in, that will give us those, that particular row and all of the column family qualifiers and values that are associated with that, right? So get is getting a single row. And if we wanted to change something, unlike SQL where we have the update command, there is no update command. It's just if you want to update something, you do a put on top of the value that already exists, right? So if we wanted to change, Christopher spelled with a CHRISTOPHER to a K or something like that, we could just put that new value on top of it. So put MG customers 103 details name and then the new value there. And now when we get that, we see that that has been updated. So yeah, this is just kind of getting us up to speed on our create, read, update, and delete operations. We've got kind of our cheat sheet here, and a lot of this stuff was gone through in the asynchronous content. As I mentioned, some nice things about HBase, the metadata, the version control that it does, that it automatically manages the regions. And this is going to be a big point of discussion in the content for next week. But like in a relational database, like when we talk about in the first week of class, we talked about how we've tried to fix scalability in relational databases through the use of sharding and replication and caching and things like that. The management of replica pairs and shards and things like that is can be very challenging. HBase just kind of automatically does all of this for us through the use and management of regions. So makes your scalability and fault tolerance really just, kind of simple to do. It's just what it does by default. And this is one of the ways in which HBase is able to get such high performance is because when it creates these regions, HBase knows the row key that a region starts with and the row key that a region ends with. Okay, and unlike a relational database, and last semester we talked about in a relational database that our tuples are not stored in any particular order, right? The tuples are just kind of randomly stored, which we said has benefits because then there is no performance penalty to reordering the tuples, okay? But unlike that, in HBase, all of our rows are actually stored in order by the value of the row key. And when these regions are created, HBase knows what the first row key is and what the last row key is, right? And so by virtue of that, when you search for a particular value of the row key, HBase immediately knows what region that's on because it knows where that value falls between the first and last row key of each region. So let's imagine you had an HBase server that had 100 regions, right? Well, since the regions since our data are stored in order by the row key, when you do that lookup, you immediately know which region it's on. You immediately, in just one operation, have eliminated 99% of the possible places that this data could be stored. You know exactly what region and then what server manages that region. And then within the region, the row keys are ordered, so it's pretty easy to look up, right? So when you start thinking about the Google scale data and potentially, trillions of things that you're trying to sort through, when you think about those trillions of elements might be stored across 1 million different regions, but then in each one of those regions, you know exactly where it starts and stops. Well, okay, it becomes a lot easier than to narrow down exactly where that one piece of data, that one needle in the haystack is located, right? So this is where we kind of get this performance when dealing with really big data. But the whole region management and automatically scaling and reorganizing of regions is a really cool thing. And there's like a time lapse of this occurring whenever I import a large data set. It's a couple of gigabytes that go in, and it automatically kind of creates and rescales the regions and things like that. All right, so the speeds. So this is where I want to look at kind of comparing and contrasting a little bit to Postgres, right? And I want to do the best I can of kind of an apples to apples comparison of a couple of different queries. So, and we'll do the same thing again next week with some more complex queries and see even more marked differences in the performance. But in AWS, I have Postgres installed on a single EC2 Elastic Compute Cloud instance that is an M6 extra large, like that's the kind of hardware class, I guess. And that gives us access to 4 CPUs and 16 gig of memory. HBase is configured on a separate cluster of 3 M6 extra large instances. So the same kind of hardware platform. And the reason it's on 3 is just because, as you might have read in the Harrison book or kind of understood from the asynchronous content, because HBase is this kind of natively distributed system, things just don't, and I tried this in a previous semester, things just don't really work right if you were on one single server. Like you have all kinds of weird stuff that starts popping up. So really the minimum number of servers you can have in your HBase environment is 3, and the recommended minimum is more like 5, and then most real implementations actually have dozens, if not hundreds or even thousands of instances coming together. But we have just 3. But the queries that we're going to be running tonight, and this is going to be different next week, but the queries we're going to be running tonight are just going to be executing on one of the 3 servers. So this isn't like a distributed query. It's something that, the way the architecture works, it will be limited to just one server. So it's kind of an apples to apples comparison. So what I wanted to look at here, so here, I've got the screen, but where's my window? There we go. So here is our connection to Postgres, and I have our U.S. counties data set that you use for assignment 1 loaded in here. So, okay, good. Everything is still connected. So if I say, select asterisk from U.S. counties, and note again, this is in Postgres, not in HBase. So we're going to be kind of comparing the two. We see our what is the number? 3,142 counties, right? So hopefully this looks kind of familiar. All of our counties in Alabama, Colorado, Georgia, Idaho, so forth and so on. The data set that you just did for assignment 1. We could do something like select asterisk from U.S. counties where county equals Harris County. And one thing you might have observed when you were doing the assignment is county names, of course, are not unique within the United States, right? We have multiple Harris counties. For example, there's a Harris County, Texas, where most of us live, and there's a Harris County, Georgia, for example, right, which is much smaller, a population of just 33,000. Or if you look for something like Washington County, there's going to be a Washington County in almost every state. 30 out of our 50 states have a Washington County, right? So county name by itself is not unique. You have to have both the county name and the state name, right? To uniquely identify a particular county, okay? So in this case, the value of county ID, which is our primary key for this table in Postgres, is 48201. And the way I have kind of set up everything in HBase is that value of county ID is going to be your row key. Okay, so I want to compare kind of the speed of Postgres and HBase here. So if I say select asterisk from U.S. county where county ID equals 48201, and we see our performance right down here in the bottom. That took 58 milliseconds, or 58 thousandths of a second. Now, I do need to give a little bit of a disclaimer here, because as I was going through this example a little bit earlier today, I was actually quite surprised by the fact that this took only 58 milliseconds, because in every semester previous, this has actually taken more like 140 or 150 milliseconds. So I'm actually kind of left scratching my head a little bit here because I haven't changed anything about this server. My guess is that something in the AWS infrastructure has in some way improved without it being something that I had to go improve. Which is actually a really nice thing about cloud computing, is that as the cloud infrastructure improves, like, you can reap benefits without having to really do anything yourself. Except in this particular case, it makes my demo just a little bit less impressive and impactful. However, we will still see a difference, right? So this took about 58 milliseconds. If we run it a couple of times, 51, 49, 50. I'm looking at this number right here. So about 50 milliseconds or so to find this one record among the 3,472 counties, or however many it is. Now, if we do kind of the same thing in HBase, we would say get from, do I call it MG or just, okay, MG US counties. Get from MG US counties, and we said the number is 48201. So we want to get this one particular record for Harris County, Texas, and we see that this took 0.011 seconds, right? Which is, just stop right here, 11 milliseconds, right? So getting this record took 11 milliseconds, 10 milliseconds that time, just 9 milliseconds that time. We're getting a little bit better every time. 11 milliseconds, 9 milliseconds, 8 milliseconds, right? So whereas identifying this one record among the 3,700 records took Postgres about 50 milliseconds, HBase right now is being about 5 times faster. It's taking it 8 to 11 milliseconds, something like that. But like I say, in previous semesters when I've done this, it's actually been more like 15 times faster, because it would take 9 or 10 milliseconds compared to 150 or so milliseconds in Postgres, which is what I kind of have illustrated in these slides here. 0.13 seconds is the same as 130 milliseconds. So yeah, it's perhaps a less noticeable difference now for whatever reason something has changed, but still HBase 5 times faster, which is nothing to sneeze at, right? I mean, it's great when something is 5 times better. I'd love to have 5 times as much money as I have right now, right? A 5 times improvement is pretty good, kind of regardless of what we're talking about or where we are starting from. And this is in a very, very small data set. I mean, 3,700 and whatever number of counties is a small data set. This is not big data. When we talk about big data, we're talking about, millions, hundreds of millions of records. And when you start getting into that size, you will see even a bigger performance difference between HBase and something like a relational database like Postgres. So in the slides here, we have a couple of examples with very similar results. So, kind of play around with that a little bit and just see. One thing I will point out that I meant to, actually, you kind of saw it happen a little bit when I did my initial scan here. So when I just did the scan of MG US counties, which, like I mentioned, is kind of the equivalent to just saying select asterisk from US counties. Certainly, this does not look very fast, right? This is taking a very, very long time to come across. And that's a little bit misleading, because what's actually taking the time here is all of that data like scrolling across the screen, okay? HBase actually retrieved that and was able to send it over the network in like a few milliseconds, 10 milliseconds, something like that. It's just the printing of it to the screen that kind of took a while in this case. So, just keep that in mind. But anyway, yeah, so this is in your slides for you to kind of reference back to. So yeah, great performance, but of course comes at a cost, because in HBase, like really all of our non-relational databases, we don't natively have the ability to do something like a join operation, right? Joins are really exclusive to relational databases. None of our non-relational databases are going to have this concept of joins, kind of with the exception of the graph database, but that's also not a join. That is the fact that we are based on this like graph data structure. So we'll come back around to that a little bit later. But we can't join. We can't do things like aggregate queries, like our average, min, max, sum, things like that, these basic statistical things that we can do in a relational database. We'll actually see next week that we can kind of sort of do that, but HBase isn't designed to do that, and there are huge performance implications for doing that. Also, we give up our data consistency and thereby our data integrity. Like, there are definitely some negatives here, right? And HBase isn't the solution to every problem, right? There are some things that a relational database is going to do better, but if your business problem is identifying a single piece of data among a tremendously huge amount of data, man, HBase will come in and save the day, right? And yeah, interacting with HBase can be both kind of simple and complex. Simple because We don't deal with joins and all these like integrity constraints and foreign key constraints and schemas and things like that, right? We don't have to design our schema beforehand. We don't deal with aggregate queries, but if we try to, it's really more of a pain. Scaling and load balancing just kind of automatically handled by Hadoop. The region management automatically handled. That's really cool. But as you get more and more into writing these queries, the syntax is kind of inconsistent and more difficult to deal with, right? When you think about the relative ease of writing SQL, select attribute from table where some condition is met, that to me is a lot more memorable and user friendly than saying scan customers, curly brace, column equal greater than square brace, name of our column family qualifiers. I don't know. That's just messy to me. Or having to type something like org.apache.hadoop.hbase.h constants : all versions, like as part of a command that you're running. Yeah, I don't want to have to type that. Especially not without like my documentation or like whatever pulled up next to me, which is why, again, I won't ask you on the exam to like reproduce code like this from memory, because I would expect in the real world that you'll kind of copy and paste this, or have done it before. Now I might show you something like this and ask you what it's going to do on the exam. And in this case, what this is doing is enabling that version control that HBase can kind of automatically do. But yeah, these are some of the things that are a little bit more complex. I do want to talk just a moment before we wrap up for the evening here in the next, 5 or 10 minutes about the case project that is coming up. So even though we are pretty early in the semester, it's not too early to start thinking about what you might want to do for the case project. So at this point, I believe we have our 5 groups established. So there were a couple of people that wanted to be placed into groups, and I handled that. And then many of you kind of established your own groups. That's great. That's less work that I needed to do to put the groups together. So hopefully you all know what group you are in and have been in communication with your group members. If you don't have a group, don't know what group you're in, don't know how to get in contact with people, reach out to me and let me know, and we'll make sure that everyone's on the same page there. But definitely, time to start thinking about it. You might want to hold off on doing any significant amount of work until after we introduce document databases on September 30th. Most groups tend to use either Postgres or MongoDB for part 1 of this case project. MongoDB comes in really handy because a lot of the big data you'll find online is in a JSON format, and JSON is kind of the native language of interacting with MongoDB. Some of the data you find online is in a CSV or kind of Excel format or something like that, which really lends itself better to Postgres in most cases. But one of those two systems tends to be what people use for the first phase of the project. HBase, usually we don't have big enough data sets to take advantage of HBase, and HBase doesn't have the analytical capabilities that most people want to use for the project. So, but yeah, never too early to start kind of thinking about what you might want to do. The project is going to be kind of similar in nature to assignment 1, except just bigger, better, cooler, more exciting, all that. And also, instead of me giving you the data and telling you what to do, it's going to be on you to find a data set, right? Import it into Postgres or MongoDB or maybe even HBase, and then determine on your own the questions you want to ask and answer, right? You're going to look at this data set and you're going to say, what is an interesting business problem that could be addressed here, right? And I mean, it's not going to come with instructions. I'm not going to tell you what to do. You have to look at this and go, how could we add value to the world? How could we kind of create new knowledge based on this data and what we're learning here, right? So you do something interesting, and then you're going to report on what you did. And in the assignment file that goes along with this, it outlines what your written report should look like, and lengths, and format of the presentation and stuff like that. So we'll get into that over the next couple of weeks. Also, as you start working on the project, I will be kind of like a consultant to each one of the groups. So you'll expect to meet with me one-on-one, or one me with one group once or twice before each phase of the project, and I'll kind of help you decide what makes the most sense, make sure we're kind of pushing in the right direction and pushing ourselves to kind of expand our skills a little bit. So it's always a lot of fun to work together on that kind of stuff. I don't have a required size for what we're going to consider like big enough big data for this, but something in the range of 10,000 up to maybe over 1 million records in the data set. Something like the U.S. counties data set with 3,000 and however many records, not big enough. We want bigger than that. The normal size that groups usually wind up with for their data set has been somewhere in the 200,000 to 500,000 record range. I have definitely had a few groups that have found data sets that were like 2 or 3 million records, and that's awesome too, but a few 100,000 records is kind of a reasonable size for what we're doing here. And if you do wind up with something really big, like a 5 or 10 gigabyte file that you need to import, check with me before we do that, just so we make sure we have the appropriate server resources and disk space and stuff. We can definitely accommodate it, but just need to make sure that we're working together and have all that in line. As far as how to find data, and you might want to start looking at this sooner rather than later, if you just do a Google search for open data or open big data or something like that, you'll find a tremendous amount of kind of freely available data sets, right? There are some large repositories like Kaggle.com, data.gov, Amazon and Google both have open data repositories that have many data sets that you can access. So a lot of great repositories like this, but then also there are a lot of organizations, states, cities, counties, things like that have like a couple of big data sets that they're hosting, right? And it's really amazing, kind of interesting, kind of scary that very often you'll find municipalities that, because they are a public service, right, and your tax dollars are paying for the services and the data that's been collected, it is freely available, right? So you might find a data set that is like a record of all of the police calls or traffic citations or parking tickets or something like that for Dayton, Ohio or whatever, right? And it's just publicly available. It's all anonymized, so there's not like citizen data on there. But like, yeah, your tax dollars pay for the police. So like the record of what calls the police have responded to is in many cases public information. So you can find a lot of big data sets like that, and traffic data and stuff like that, which is really cool. So you'll be amazed at what you will find out there when you start digging a little bit. There are kind of some things to look out for. Sometimes this data can be in like really weird formats. Like I've seen things where the data is like spread across 30 different Excel files or 30 different CSV files, and every one just has like 3 attributes in it or something, and you got to like combine all that together to use it. And maybe that's easy enough to do, and it's interesting enough to do that. Or maybe you look at that and you go, I'm going to find a different data set to use. I don't want to go to all this trouble. So some can be in weird formats. Some is very straightforward. Some of it starts out interesting looking. There was a data set I found about like lightning strikes, like where, it recorded where the Geological Society or whatever whatever it is, had recorded like all the lightning strikes in the U.S. over the past however many years. Like, oh, that's really cool. But then it's really just a giant list of like latitude and longitude and timestamps. And I'm like, oh, well, I don't know what I'm going to do with this that's actually interesting. Some of these data sets are more geared toward like AI training and machine learning and language models and stuff like that, and don't really lend themselves to like business problem analysis. So probably you're going to want to start by identifying maybe like 5 or 10 or more possible interesting data sets and kind of evaluate what makes sense for this particular project would be my advice here. Also, sometimes you'll find data that is behind a paywall or that you have to pay to access. It might be a few dollars, it might be a few $100s. If you really want to purchase data for this project, that's fine with me. I don't think that's going to give you any advantage, but I certainly wouldn't recommend it because there is just an embarrassment of abundance of free data online. So yeah, no reason you should have to pay for or subscribe to or whatever to get access to some data. Previous semester's topics, we've had projects from all of these different things. There are a lot of like food, nutrition, and health and exercise data sets. There's a lot of, especially in the wake of COVID, a lot of like disease and contact tracing data sets. There's a lot of data sets around mortality rates around different diseases and things like that. So a lot of health-based stuff. Technology, gaming. There's a lot of data sets that come from like the Apple, Apple Store and Google Play Store and stuff like that. YouTube data sets, gaming review site data sets. There's dumps from Facebook and Twitter and LinkedIn and stuff like that. So a lot of social media analysis that can be done. Like I mentioned, many cities and municipalities have public data sets that they posted about police interactions and traffic patterns and stuff like that. Real estate, travel, there's a lot of data sets out there that are like Airbnb and VRBO reviews, weather, climate, music, movie reviews, sports. A lot of groups like to do analysis on sports, right? You've got statistics about every player on every team, every game, every inning, every down that's been played for the last 50 years. So there's a lot of cool stuff you can do there. Stock market data, finances, cryptocurrency, right? All kinds of options of what you can do here. So hopefully among all of these topics, something has kind of sparked your interest a little bit, and perhaps you'll do something that's not part of what I'm describing here, and next semester I'll be able to add even more kind of categories to this list of projects that students have done in the past. So definitely start thinking about that a little bit, and I'll be reaching out to all the groups probably in about 2 weeks or so, or maybe after we introduce MongoDB, to start setting up some meetings to kind of discuss with me about what it is you are going to be doing. So any questions, comments, concerns about the case project stuff? All right, well, that is kind of a wrap of the content we have for this week. For next week, the videos are going to focus on programmatic interactions with HBase. So there's a couple of small Ruby programs that are provided to you that will kind of go through how we can programmatically insert like multiple values at a time, things like that. We're going to get deeper into the HBase architecture and the scaling and the regions and things like that, and then show how we can interact with HBase in a more SQL-like manner using this language called HQL, or Hive Query Language. Video series 5 is about 1 hour and 10 minutes worth of videos, so we'll be, again, about 1.5 hours or so next Tuesday night. Remember to complete the progress quiz that we just had the 5 questions for a couple of minutes ago by Friday at 6 p.m. And if you did all the reading for this week in both the Perkins and Harrison book, there is no additional reading for next week. It was all kind of in those chapters that you've already read. Also, no assignment due next week. So we have a kind of a lighter load of outside of class stuff this week. But of course, next week, once we wrap up HBase, we'll have our second assignment, which will have you working inside HBase. So that's what we've got coming up. That's what I've got for you tonight. So if there are any final questions, I'm happy to address those. Or if you want to send me an email and I can address them later, that works as well. But if not, y'all have a great rest of your evening. Go forth and do great things. And I look forward to seeing you again next week.